today we consider the decomposition algorithm, and we explain this decomposition algorithm using this example. Now this problem is a linear programming problem. It is a maximization objective with 4 variables and 6 constraints and all xj greater than or equal to 0. We can solve this using any of the techniques of linear programming that we have learnt till now, but we are going to introduce a newer version of simplex or a new technique which is called the decomposition algorithm, which is going to be used to solve this problem. Let us take a closer look at this set of constraints. Now there are 6 constraints, but we observe that the first 2 constraints involve only the first 2 variables. The next 2 constraints involve the next 2 variables x3 and x4, and these 2 constraints have all the variables. So one of the things we can do is that if we relax the problem, which means we remove some of the constraints by relaxing the problem, if we relax these 2 constraints and look at only the other 4, now we realize that this problem can be split into 2 linear programming problems, which one of which will be maximize 6x1 plus 5x2 subject to these 2 constraints, and the other will maximize 3x3 plus 4x4 subject to these 2 constraints. So by removal of a certain number of constraints from the problem, or by relaxing the problem by removing the constraints, the given problem now can be decomposed into more than one linear programming problem, more than one independent linear programming problems. So we exploit that idea. So first thing is that if we remove these 2 and solve the resultant linear programming problem, and if it turns out that the optimum solution to the resultant problem satisfies this, then it is also optimum to the original problem. More often than not, that will not happen. So we will also have to consider these 2 constraints. So the method that we will adopt is first remove these 2 constraints, treat them as 2 independent problems, and then ensure that the solution obtained to those independent problems now also in some way or the other meet these constraints, so that the optimum solution can be obtained. Now before we even proceed further, let us see why we are doing this. If we were to solve this as a linear programming problem, every iteration of the simplex method would involve all the 6 constraints. So it would involve 6 basic variables, and every iteration is to invert a 6 by 6 matrix. But if on the other hand we remove these 2 and then decompose the problem into 2 problems, each having 2 constraints, then in each iteration we are inverting, in principle we are inverting a 2 by 2 matrix. So we are actually inverting 2 2 by 2 matrices. But we also have to have some relationship between these constraints and the other one, and therefore there is one more binding constraint that is added. So effectively we will be looking at 2 plus 2 plus 3. Original problem has 6, but then we will be looking at 2 plus 2 plus 3, but we also understand that inverting a 6 by 6 matrix is a little more computationally intensive compared to inverting a 2 by 2, another 2 by 2 and another 3 by 3. So the computing time required to solve this problem becomes lesser, particularly when we write computer programs and solve. Now these 2 constraints which are taken out are called the master problem constraints. So these are called the master problem constraints. And these 2 are the sub problem constraints, which we call as 1 and 2. So this is a sub problem constraint, this is another sub problem constraint, and so on. Now the 2 sub problems are maximize 6x1 plus 5x2 subject to this and maximize 3x3 plus 4x4 subject to this. Actually in every iteration we need to solve this as well as solve this. Instead what we will do to make our computation simpler, we will simply note down the corner points associated with this and the corner points associated with this, so that depending on the objective function, which we will see will modify slightly, depending on the objective function, by a simple substitution of the corner points we can get the optimum solution quickly, because we are illustrating this on the blackboard in a classroom environment. Ordinarily every time the sub problem is solved, it should have been solved by the simplex algorithm. So let us first identify the corner points associated with this and the corner points associated with this. Because it is a 2 by 2 problem, we can actually solve it by the graphical method and try to find out the corner points. So the first set of corner points, to do that we have x1 plus x2 so this is x1 plus x2 equal to 5. Now 3x1 plus 2x2 equal to 12 will look like this. So this is a corner point 4 comma 0, this is the corner point 0 comma 0, this is the corner point 0 comma 5, and this will be the corner point 2 comma 3. So these are the 4 corner points associated with this. So we will simply write the 4 corner points for our reference here: 0 0, 4 0, 0 5 and 2 3 are the 4 corner points associated with this. Now let us find out the corner points associated with the second one. This will be the x3 axis, this will be the x4 axis. X3 plus 2x4 less than or equal to 8. x3 plus x4 less than or equal to 10. So this will be the point 5 comma 0, this is the point 0 comma 0, this is the point 0 comma 4, and this will be the point 4 comma 2, this will be the point 4 comma 2. So the 4 corner points associated with this are 0 0, 5 0, 0 5, 0 4 and 4 2. So these are the corner points associated with. Now let us understand one more principle before we apply the decomposition algorithm. Now suppose we have a feasible region like this. For a given problem, let us assume that this is the feasible region. Now if we add a constraint into this problem, the first thing that can happen is the feasible region can reduce or the feasible region will remain the same. These two things can happen. Now let us assume that the feasible region reduces. So let us say the feasible region comes somewhere here because of the additional constraint. Now if this were the optimum solution before the introduction of the constraint, and because of the introduction of the constraint, this optimum solution becomes infeasible. Now once again it has to be in one of the corner points. Now the new optimum solution has to be in one of these corner points, in these 5 corner points now that we have. Now if this were the optimum solution, then this was not a corner point in the first case when the new constraint was not added, because the corner point was here. Now this point, if it is the optimum solution, can always be represented as a convex combination of this point as well as this point, because of the convexity property of the feasible region to a linear programming problem. So, any point on the feasible region can always be represented as a convex combination of one or more corner points. If we expand it to higher dimensions, then it becomes convex combination of one or more corner points. For example, this point can always be represented as lambda 1 into this plus lambda 2 into this, where lambda 1 plus lambda 2 is equal to 1. Similarly, any point inside can also be represented as a convex combination of the given corner points. So, as we add more and more constraints in, the feasible region can reduce, and the final optimum solution can even be a point which is inside this and need not be on the boundary. So, since any point inside the region can be represented as a convex combination of corner points, it is enough to look at those corner points and try and identify which of the corner points are finally going to be part of that combination, which will eventually give the optimum solution. So, what we can do is, if we, let us say we kind of remove this, so we get this feasible region whose corner points are known here. By the addition of these two, the optimum solution is going to come into some point inside the feasible region which is bounded by these corner points. But please note that these corner points are given as x1, x2 and x3, x4, even though the solution to this, each point has its own x1, x2, x3, x4. The fact is, by the addition of these two, if the optimum shifts and comes to a point inside the region, it still can be represented as a combination of these corner points that we are going to have. So, that is another idea that we will use in the decomposition algorithm. Now, let us look at some little bit of theory with respect to the decomposition, and then we proceed to solve this problem. So, let us assume that the given problem is actually a minimization problem. Minimize Cx. Our example is a maximization. We will see later how we modify this, but right now let us look at a minimization problem, which is of the form minimize Cx subject to Ax equal to b, Ax equal to b, and x is an element of x. What do we mean by that? What we mean by this is, if we take this example, this is a maximization problem, but this can be written as a minimization problem by simply saying minimize minus 6 x1 minus 5 x2 minus 3 x3 minus 4 x4. I have not even written x greater than or equal to 0, I also have to explain what is this x and what is this x. So, we could use, let us call this as some small x, minimize Cx, Ax equal to b, x belongs to x. Let us do that. Let us use this notation that way. Now, when we apply this to this, the minimize Cx is intact, because that is the same as this minimize minus 6 x1 minus 5 x2 minus 3 x3 minus 4 x4. Now, Ax equal to b are actually the master constraints. So, these two are the ones that are associated with this Ax equal to b. Now, x is an x belongs to x means, it simply means that this x represents the set of corner points of these two. So, in some sense x belongs to x comes out of this. So, if we consider this problem minimize Cx subject to Ax equal to b, x belongs to x, this is the master problem constraints and these are the corner points of the sub problems. Now, we have also said that now every point is going to be represented as a convex combination of the corner points. So, what we are going to do is this x will be written as some lambda j x j, where x j are these corner points. So, when we write this, the problem will now reduce to minimize sigma C j lambda j x j subject to a lambda j x j less than or equal to b, sigma lambda j is equal to 1. Because it is represented as a convex combination of the corner points. For example, here when we said that this can be written as lambda 1 x 1 plus lambda 2 x 2, where x 1 and x 2 are corner points, lambda 1 plus lambda 2 is equal to 1. This can also be written as lambda 1 x 1 plus lambda 2 x 2 plus lambda 3 x 3, lambda 1 plus lambda 2 plus lambda 3 equal to 1. So, when we start representing, introduce a lambda and start representing it as a combination of the corner points, we need the linking constraint, which is sigma lambda j equal to 1. And since every point inside this region also has to satisfy the master constraints, so the point itself is lambda j x j, so it will satisfy the constraint sigma a lambda j x j less than or equal to b or equal to b, depending on how the problem is defined. When we say here, when we say it is equal to b, it means the inequalities have been converted to equations. Here we simply retain the inequalities as it is. You may say plus a slack variable equal to b or plus a surplus variable if it were a greater than or equal to constraint. Therefore, the problem reduces to something like this. Now, for this problem, we can actually, now this is the problem that we are actually trying to solve. The only difference being all these xj's are corner points which are given here, and any point x inside this region which actually satisfies this set of constraints, optimizes this objective and has this lambda, now is the solution to the problem. So, the problem now becomes one of not solving for the xj's, but solving for the lambdas. The lambdas now become decision variables, because the xj's are known corner points. These are the corner points. So, the lambdas become the decision variables for this. Now, this one I have written in a certain form. We may put a summation here. So, in which case we can put aij lambda j x j sigma aij lambda j x j is equal to bi. We can put it that way. We can either write it as individual constraints or keep the whole thing as a vector. But in principle, what I am trying to explain here is that these xj's are the corner points, and any point inside which will be the solution is now represented as sigma lambda j x j, and therefore, this problem gets rewritten in this format. I have also explained this equation versus inequality. When I write an equation here, I assume that the inequalities have been already converted to an equation by the addition of suitable slack variables or surplus variables. When I write an inequality here, I assume that we are yet to add the slack variable or the surplus variable. Or if we want to be consistent with these two, we can even say that xj equal to bi, which means that we have added the slack variables and surplus variables associated with this. Now, as I said, the focus now shifts on finding out the lambda j which become the variables, or which are essentially the weights that are associated with each corner point. So, we now start solving this problem first. Now, we can start solving this problem by doing a few things. If we are able to get a feasible solution to the problem, for example, all these constraints, this is a convenient example where all these constraints are less than or equal to constraints. Therefore, the point 0 0 0 0 is basic feasible for this, particularly when we leave out both these. We have 4 constraints and the point 0 0 0 0 is basic feasible. So, we could start with lambda 1 equal to 0 0 0 0, which is a corner point. So, we can start with lambda 1 for this. Now, these two are the master problem constraints, and these two constraints are also less than or equal to constraints. So, the corresponding slack variables can be added here. So, we can add an S1 here and we can add an S2 here. So, S1 and S2 automatically qualify to be basic variables. So, we can start solving this problem with a basis which comprises of S1, S2 and lambda 1. So, the first basis that we can have for this is given by S1, S2, lambda 1, still have S1, S2, lambda 1, and right hand side we will have the identity matrix 1 0 0, 0 1 0, 0 0 1 with values bi are 7 and 17. So, the right hand side values are 7 and 17, and for this constraint the right hand side value is 1. So, it is 1, and we have also defined lambda 1, which is our first starting point, to be 0 0 0 0, which comes out of these two. Now, because we have a basic feasible solution with 0 0 0 0, we can start this. Otherwise, we may have to introduce an artificial variable for this and then begin with the artificial variable. Right now, since we are going to solve this numerical example and the point 0 0 0 0 is basic feasible, we simply start with a lambda 1, which is 0 0 0 0, which takes weight equal to 1. So, the current basic feasible solution to the problem is actually the solution 0 0 0 0. Now, we have to find out Cj minus Zj or Zj minus Cj, which will be 0 0 0 and 0 here. Now, this is a starting basis as far as this problem is concerned, which means this basic feasible solution has one corner point, which is the point 0 0 0 0, and right now this has a solution with z equal to 0. So, if we substitute 0 0 0 0 here, we will get the solution z equal to 0. Now, we need to verify whether this solution is optimal. Now, in order to verify whether this solution is optimal, we need to find out whether there is an entering variable. Now, we have not written the entire table, we have written only that part of the simplex table which contains the basis matrix B, the right hand side, and the Zj minus Cj under B, which can always give us the dual variables. We know by now that Zj minus Cj, the notation that we have used, particularly in the earlier course on the fundamentals of OR, where we covered linear programming extensively, we also mentioned that if we use Zj minus Cj and if we do not have artificial variables, now exactly under the identity matrix, the beginning identity matrix, we can always read the solution to the dual of this problem. So, this helps us in reading the solution of the dual directly. Now, we need to know what are all the other columns corresponding to the different non-basic variables. Let us also remember right now, which something we said earlier, that the variables are not xj's, but the variables are the lambdas. So, each lambda is associated with a corner point. Now, several corner points are possible. In fact, right here there are 4 here and there are 4 here. So, 16 corner points are possible. Now we have to check for all the 16 Cj minus Zj's, and if they cannot enter, then we have reached the optimal solution. So one way is to generate all the 16 and then try and find out the Cj minus Zj associated with all the 16. If for example we had a much larger problem, if for example it was decomposed into 3 sub problems, and let us say there were 5 corner points in each, then you are looking at 5 into 5 into 5, 125 variables. So we do not want to store all the corner points and then verify whether these corner points can enter. Instead what we do is we try and follow the column generation idea that we saw in the cutting stock problem, and then check that if there is a corner point that can enter the basis, if there is a lambda that can enter the basis, because each corner point is associated with a lambda. So if there is a lambda that can enter the basis, we now generate that corner point and say that this corner point can enter the basis with a certain lambda. So we follow the column generation idea and we do not explicitly store all the combinations of the corner points. Now how do we generate an entering corner point or an entering lambda? So in order to enter, we need to make sure that Zj minus Cj, so it is a minimization problem. So Zj minus Cj, since it is a minimization problem, a positive Zj minus Cj will enter the basis. We have seen for a maximization problem, a positive Cj minus Zj will enter. For a minimization problem, a positive Zj minus Cj will enter. Please remember, we have defined this problem as a minimization problem. It is only incidental that our numerical illustration is a maximization. But if the problem is a minimization problem, then a positive Zj minus Cj will enter. So if there is a j, if there is a corner point whose Zj minus Cj is greater than 0, then such a j can enter. Now what is the Zj? Now Zj is equal to Ypj. Zj is always equal to CBB inverse Pj. So that will be equal to Ypj minus Cj is greater than 0, where y is the associated dual variable. Now in this problem, if we look at this primal, here we have as many constraints as the master constraints, and in our illustration two constraints. So this will give rise to 2 dual variables. This is always a single constraint, so this will give rise to 1 dual variable. So we will now instead of calling the dual variables by y, which is the customary notation, we would now introduce dual variables w and alpha, where since there are 2 constraints here, we will have w1 and w2, and there is 1 constraint here, so we will have alpha. So what happens here is, so this y becomes w alpha. What is Pj? Pj is an entering column, Ypj, CBB inverse Pj. So Ypj is an entering column, and the entering column right now, any entering column here will be of the form Axj1, because the lambda j is the variable. So you need to take this variable outside. So the entering column will be of the type Axj1. So you will have W alpha into Axj1 minus Cj should be greater than 0. And this is Cj now becomes Cjxj from here, because lambda j is the variable. So Cj becomes Cjxj greater than 0. Let me explain this again. Now in order for a new variable to enter the basis, because it is a minimization problem, in general Zj minus Cj should be greater than 0. In general, Zj is written as Ypj minus Cj greater than or equal to 0, where y is the dual variable, Pj is the entering column, and Cj is the objective function coefficient of the entering variable. Now, all these are general equations. Now, we are adapting this to the problem on hand. Now, because our problem is structured specifically this way, now there are as many constraints here as in the master problem, which are 2. So, introduce dual variable w, which will be w1, w2, w is a vector. This is always a single constraint, so introduce an alpha. So, y becomes w alpha. Now, if there is an entering lambda j is the variable, xj is not. So, if there is an entering lambda j, then the coefficient will be a xj 1. So, we will get a xj 1. Remember that this is in matrix, this is a single thing. So, there will be 2 w's, there will be 2 values coming here. There is 1 alpha, there is just a 1, minus the Cj is the objective function coefficient of the entering variable. So, the entering lambda will have an objective function coefficient of Cxj or Cjxj, Cjxj greater than or equal to 0. Now, this can be expanded to Wa minus C into xj plus alpha greater than 0. Now, we also know that this xj is a corner point corresponding to this and this, because every x is written as lambda j xj, where xj is a corner point. Therefore, because xj is a corner point, xj has to satisfy this and this set of constraints. So, what we want to do now is, if there is an xj which satisfies this and this and has a value Wa minus C xj plus alpha greater than 0, then such an xj can enter the basis, such a corner point can enter the basis with an associated lambda j. So, we do the usual thing of this being strictly greater than, we say that we now want to maximize Wa minus C into xj subject to xj belongs to some x, where this x is the set of corner points, and then we find out such, so we find out such an xj and then enter the corresponding lambda j into the solution. Now, this is equivalent to solving the 2 sub problems. For a given objective function, this is equivalent to solving the 2 sub problems. So, with this bit of theory, let us go back and see whether there is an entering corner point whose lambda has to enter the basis. So, to do that, we go back and now check, we want to find out Wa minus C into xj plus alpha. So, let us write this Wa minus C now. From this solution, we also said that this being a simplex table and this being the identity matrix, there are no artificial variables and we are computing Zj minus Cj. Zj minus Cj will automatically give us the values of the dual. So, these 2 values will be W1 and W2 because they correspond to S1 and S2. S1 and S2 were obtained from this, and W is the dual variable for this. So, W1 and W2 are seen here, alpha is seen here, alpha corresponds to this, alpha corresponds to this lambda 1, so alpha is seen here. So, from this, right now the W's are all 0, so we want to maximize this. Right now the W's are all 0, so W A minus C xj, Wa minus C xj, they are all 0 plus alpha. So, right now we will have maximize minus C xj, alpha is also 0. So, maximize minus C x j. Now, remember the original problem is minimize C x. So, this problem has to be written as minimize minus 6 minus 5 minus 3 minus 4. So, C is the C vector is minus 6 minus 5 So, this is C because the given maximization problem has to be written as a minimization problem because the theory this is derived for a minimization problem. So, the C vector becomes minus 6 minus 5 minus 3 minus 4. So, maximize minus C x j will now become maximize 6 x 1 plus 5 x 2 plus 3 x 3 plus 4 x 4 subject to x belonging to this. So, this is decomposed into two problems. The first problem being maximize 6 x 1 plus 5 x 2 subject to this constraint, and the second one is to maximize 3 x 3 plus 4 x 4 subject to this constraint. So, we now have to solve two linear programming problems. One is a 2 by 2 problem, the other is a 2 by 2 problem to get the solution to this, subject to the condition that x j belongs to corner point. Because these two are linear programming problems and we know the corner points of the feasible region, ordinarily this is not the best way to solve this. Each one has to be solved as an LP as we go through the iterations, but because we are solving a much smaller problem and each of the sub problems has only two constraints and it is a 2 by 2, we have simply stored the corner points just to make the ease of computation possible for us. But in practice, when we are actually solving a very large LP, we will not a priori compute all the corner points and keep it. So, at every stage we will be solving a linear programming problem within the decomposition. So, let me again repeat, only to make the computation simple I have just written down all the corner points. Since we know all the corner points, we can go back and find out what is the best value. So, 0 0 will give 0, 4 0 will give 24, 0 5 will give 25, 2 3 will give 27, 6 into 2 12 plus 5 into 3 15. So, this gives the optimum solution 2 3. Second one is 3 x 3 plus 4 x 4. So, 3 x 3 is 15, here it is 16. Now, 4 into 3 12 plus 2 into 4 8 is 20. So, 4 2 is optimal from this, 4 2 is optimal, this is 27, this is 20. So, z is equal to 47. So, value of z is equal to 47 and the corner point 2 3 4 2 enters the basis. So, the first corner point that will enter the basis is lambda 2, which is 2 3 4 2. So, we now know the entering corner point, which is 2 3 4 2, but we have to find out the leaving variable. Now, in order to find out the leaving variable, we need to find out p bar j. So, p bar j is equal to B inverse Pj, and this is always B inverse. So, this is B inverse. So, p bar j equal to B inverse Pj. Right now, B inverse is I. So, p bar j is equal to Pj, and what is Pj? Pj, any entering Pj is Axj 1. So, this is Pj, this is equal to Axj 1. So, now we have to compute Axj and 1. Now, Axj is equal to, now A comes from the master problems. Please note, this is the master constraint, this is the Axj equal to B. So, this is the master constraint. So, A is 1 1 1 1, 2 2113, 1111, 2113 into xj is 2342. So, this gives us 2 plus 3 5 plus 4 9 plus 2 11, 4 plus 3 7 plus 4 11 plus 6 17. So, AXJ1 is 11, 17 and 1. Now, we have found out the entering column which is P bar j. So, we just write the entering column here. So, this is our lambda 2 which is 11, 17 and 1 with value equal to 47, because the positive Zj minus Cj will enter the basis. So, this enters the basis. So, lambda 1 with lambda 2 with 11, 17 and 1 enters the basis. Now, we have to find out the leaving variable, and to find out the leaving variable we will compute a theta. Note that theta is right hand side divided by the entering column. So, it is 7 divided by 11, 7 divided by 11, 17 divided by 17 and 1 divided by 1. So, minimum theta leaves the basis, therefore, this will leave the basis and this is your pivot element. Now, we need to perform one simplex iteration. So, we will go back here to continue with the simplex iteration. Now, the variable S1 is replaced by the variable lambda 2. So, you have lambda 2, S2 and lambda 1 with Zj minus Cj. Now, divide every element of the pivot by the pivot element. So, we need a 1 0 0 here. So, divide by the pivot element. So, you get 1 by 11 0 0, 7 by 11 1. Now, we need a 0 here. So, this minus 17 times 1 will give me 0. So, 0 minus 17 into 1 by 11 is minus 17 by 11, 1 0. This minus 17 times this, 17 sevens are 119. So, 17 minus 119 by 11. So, 17 into 11 is 187 minus 17 minus 17 into 7 by 11. So, this is 187 minus 119 by 11, which is 68 by 11. So, we get 68 by 11 here. This will become 0 and we need another 0 here. So, this minus this will give us 0. So, minus 1 by 11, 0, 1, 1 minus 7 by 11 is 4 by 11 and a 0 here. We also know that we can do the same kind of row operation to try and get the new Zj minus Cj. So, what we need is a 0 here. So, this minus 47 times 1 is 0. So, this minus 47 times is minus 47 by 11, 0, 0. This minus 47 times, so 47 into 7 is 329. So, we get minus 329 by 11. Now, this is the solution. Now, what does this basic feasible solution tell us? Now, right now from 0 0 0 0 this has moved to a new point which is given by lambda 1 is equal to 4 by 11, lambda 2 is equal to 7 by 11, which means the present point that we are looking at, is 4 by 11 into 0 0 0 0 plus 7 by 11 into lambda 2, which is 2 3 4 2. This is all 0. So, the point is 14 by 11, 21 by 11, 28 by 11 and 14 by 11. This is the point we are right now looking at. What is the value of the objective function? 6x1, 14 6 are 84, 5x2, 105 plus 84 is 189, 28 into 3 is another 84. So, 189 plus 4 193, 273, 273 plus 56 is 329. So, we get 329 by 11, which is the value of the objective function right now. So, from here we have moved on to one iteration, and which means from the corner point 0 0 0 0 we have now moved to a corner point 14 by 11, 21 by 11, 28 by 11, 14 by 11 if we look at the entire problem. But we have not looked at the entire problem at a time, we have arrived this corner point in a slightly different way by getting this as a convex combination of two corner points 0 0 0 0 and 2 3 4 2 with weights 4 by 11 and 7 by 11. Now, also when we reached here, we have actually generated an entering column by solving a sub problem. The sub problem turned out to be solving two independent linear programming problems in this case. So, we did not store all the corner points. Now, we need to check whether this corner point is optimal, and in order to do that we need to check whether any other lambda can enter the basis. For any lambda to enter the basis, we again need to find out maximize WA minus C x j plus alpha subject to these two sets of corner points or subject to the x j satisfying this and this, both mean the same. So, we now go back and try to solve these two sub problems. From this we know that now W is minus 47 by 11 comma 0. So, W is minus 47 by 11 minus 47 by 11 comma 0 into A is 1 1 1 1 2 1 1 3 1 1 1 1 2 1 1 3. So, we are first finding out WA. So, this is minus 47 by 11 minus 47 by 11 minus 47 by 11 minus 47 by 11. This is WA, because 0 into 2113 is 0. So, WA minus C is equal to minus 47 by 11 minus 47 by 11 minus 47 by 11 minus 47 by 11 minus C is minus 6 minus 5 minus 3 minus 4 minus 6 minus 5 minus 3 minus 4 plus alpha, and alpha is right now at 0. So, we go back and simplify this. So, this is 6 minus 47 by 11. So, this is 19 by 11, 66 minus 47 is 19. Now, this is 5 minus 47 by 11, which is 8 by 11. That is 3 minus 47 by 11, which is minus 14 by 11, and 4 minus 6, 5, 3 and 4 C values are minus 6, minus 5, minus 3 and minus 4. So, 4 minus 47 by 11 is minus 3 by 11. So, we now have to solve a problem which maximizes 19 by 11 x 1 plus 8 by 11 x 2 minus 14 by 11 x 3 minus 3 by 11 x 4 subject to these two constraints. So, the sub problem that we generate now is decomposed into two linear programming problems, which again have to be solved separately by using the simplex algorithm. But as explained earlier, since these are all small sized problems, we have stored the corner points, and by substituting the corner points into this, we can find out the objective function value and the optimum solution. So, when we look at 19 x 1 plus 8 x 2 and minus 14 x 3 and minus 3 11 x 4, so it is fairly obvious that 0 0 is an optimum solution to this. You are maximizing minus 14 by 11 x 3 minus 3 by 11 x 4, which is minimizing that. Therefore, 0 0 is optimal here. As far as this is concerned, we look at 19 x 1 plus 8 x 2 to begin with. So, this would give us 0. This is 19 4s are 76, this is 8 5s are 40, this is 19 2s are 38, 38 plus 24 is 62. So, the point 4 comma 0 is optimal here. So, 4 comma 0 is optimal here. So, this has 76 by 11, this is 0. So, with z equal to 76 by 11 we enter. So, the point 4 0 0 0 enters the basis with z equal to 76 by 11. So, what we do now here is we enter this point 4 0 0 0 into the basis, but before we enter that we have to find out p bar j, and then we need to enter. So, p bar j is equal to b inverse p j. So, p bar j is equal to b inverse p j, and in order to find out p j we need to do a x j 1. So, p j will be, so first we do a x j. So, a x j is 1 1 1 1 2 1 1 3 into 4 0 0 0, which is 4 and 0, 4 and 8. One into 4 plus 1 into 0 plus 1 into 0 plus 1 into 0 is 4, 2 into 4 is 8. So, we get 4 and 8. Now, a x j 1, which is p j, is 4, 8 and 1. Now, p bar j is equal to b inverse p j. So, p bar j is equal to b inverse p j. This is b inverse can always be read from this. So, 1 by 11 minus 17 by 11 minus 1 by 11, 0 1 0 0 0 1 into 4 8 1. This would give us 4 by 11 minus 68 by 11 plus 8, which is 20 by 11. This is 88 minus 68 is 20 by 11. This is minus 4 by 11 plus 4, which is 40 by 11. So, minus 4 by 11 minus 4 by 11 plus 0 plus 1. So, minus 4 by 11 minus 4 by 11 plus 1 is plus 7 by 11. So, you get plus 7 by 11. So, now the corner point 4 0 0 0 which will take a value lambda 3 will enter the basis with the entering column 4 by 11, 20 by 11, 7 by 11 and with Zj minus Cj value of 76 by 11. So, let us enter that. So, what we do now is we kind of keep this column as some kind of a dynamic column, because what we got from here is already available here. So, I will erase this as well, and I will notionally say that another lambda 3 is entering the basis here. So, lambda 3 is entering the basis with values 4 by 11, 20 by 11 and 7 by 11, and with a positive Zj minus Cj value of 76 by 11. Now, we need to find out, now we know that variable lambda 3 or corner point 4000 enters the basis using a variable lambda 3, and we now need to find out the leaving variable. Now, the leaving variable could be any one of these three, which is found out by the minimum theta rule. So, a minimum theta is right hand side divided by the entering column. So, 7 by 11 divided by 4 by 11 is 7 by 4, 68 by 11 divided by 20 by 11 is 68 by 20, which is 34 by 10, which is 17 by 5, and this is 4 by 7. Now, clearly 4 by 7 is the minimum of the 3, because this is more than 1, this is more than 3 and this is less than 1. So, this variable leaves the basis. So, when this variable leaves the basis, we need to perform one more simplex iteration, where we replace lambda 1 with lambda 3 and continue with the simplex algorithm. But before we continue with the simplex algorithm, let us again take a very quick recap of what actually has happened. So, what we did was, in this we started with this large linear programming problem, and we realized that by leaving out a certain set of constraints, the problem is decomposable into smaller sized problems. So, those constraints that go out constitute what is called the master problem, and the others constitute the sub problem. We also exploited the convex combination property, and then we rewrote the formulation this way. Now, based on this formulation, we have been carrying out the simplex algorithm, and we have come up to the variable lambda 3. We will continue this discussion in the next session.